In today's repetition course, we will have a look at the stabilization of carbon ions. Let us start with trifluoromethane. A base will deprotonate. We will get to this trifluoromethyl anion, and this should be stabilized simply because we have those fluorine atoms sitting here with a high electronegativity. Therefore, those carbon fluorine bonds are polarized to the fluoride, and this will stabilize the anionic charge. So, stabilization by an inductive effect. However, if this anion loses fluoride, then we get to this difluorocarbene. This is interesting because this would dimerize, giving rise to tetrafluoroethane, which is the monomer of Teflon. Could then be polymerized and so on. Well, the same should happen with chloroform, the trichloromethane. If we take, for instance, potassium hydroxide, then we know that water will be formed by deprotonating here that proton, and then we have that again this anion, a trichloromethyl anion with a potassium cation present. Potassium chloride will be formed as a salt, and the dichlorocarbene that could give some reactions, as we know, the dimerization or the formation of a three-membered ring by reaction with an olefin. So, again, a stabilization by an inductive effect, because the chlorine atoms are also rather electronegative, not as electronegative as the fluorides. So we find a pKa of 15.7 that says, well, this acidity is lower compared to nitromethane. Here we have an acidity that is, well, 10,000 times, more than 10,000 times higher compared to chloroform. Why is this the case? Well, if we deprotonate here, then we get by the alpha acidity that an ion, this is stabilized by this highly electronegative nitro group. Also, this bond is polarized here. But in addition, we have the possibility for a stabilization by a mesomeric interaction. So, we have this mesomeric structure with a positive charge here and two negative charges at the oxygens. So the truth is in between. We have a rather strong double bond character between the carbon and the nitrogen. So how could a compound look where the corresponding anion is even more stabilized? Well, if we have the possibility to find mesomeric structures to two carbonyl groups, as in this case, it is stabilized mesomerically to one carbonyl group here and also to the other carbonyl group. On the other hand, we can say this compound called dimidone, there is this methylene group double activated because it is in alpha position to 2 carbonyl groups, and indeed with a pKa of 4.2, this is even far more acidic here compared to the nitromethane. So most interestingly, we can have a look at the pKa of that trifluoromethane, and there we will find some surprising information. We have a pKa of higher than 25. Well, just from the electronegativity, we would say this should be better stabilized than that, than the chloroform, the corresponding anion of the chloroform, since the fluorine atoms are more electronegative than the chlorine atoms. But what could be the reason? Well, the carbon-fluorine bond is significantly shorter compared to the carbon-chlorine bonds. That means that the fluorine atoms with that high electron density here are more close to the carbon and therefore more close to that anion, and well, the close proximity of all those electron pairs is destabilizing this system, and the lower acidity is the result. Well, how can we improve this scheme? Well, I have written simply base here because potassium hydroxide is not basic enough to smoothly deprotonate the trifluoromethane. While we could use LDA for deprotonating, then we would get a lithium countercation sitting here, covalently bound, and this would then rapidly eliminate lithium fluoride to give that carbene. So another improvement, while in both reactions here there is that subsequent reaction pathway to the carbenes, well, here the reaction goes in this direction. In these two cases we could also add such an arrow to symbolize that in these two cases we have clearly equilibrium reactions. Thanks for listening.